our first periodic trend we're going to look at is atomic radius. Sorry, I lied before. I am going to put one more little diagram on this, but it's only a short one. So in the book, it describes atomic radius as the distance between a nucleus and the edge of its electron cloud. That's not actually how it's measured. It's not actually how we do that in the real world, because you can't do that. You can't find those electrons. So it's actually, while it's not an incorrect description, it's not how we work it out. For metals, we look at the metallic lattice or metallic structure, and we measure the distance between nuclei because we can do that. And I believe that it's with X-rays. X-rays bend or diffract when they go through small gaps, and we can measure the effect of that to infer the distance between two nuclei. Then we just split that in half, because that would have to be the radius. Halfway between those must be the radius. So that's how we work it out for a metal. For a non-metal, most of those can be turned into a molecule or, like diamond, a 3D network. And so what we do is look at the distance between two nuclei that are bound covalently, and again we split that in half. And that would therefore have to be surely the distance between the outermost electrons and the nucleus. So that's how it's worked out. But when we describe it, it is the distance from the nucleus to the outermost electrons. So there are a couple of factors that affect how big or small an atom is. They're not all the same size. Not surprisingly, hydrogen is the smallest atom. Not surprisingly, when we get down to something like gold, which is down in this 2, 4, 6th period in the periodic table, they're really big atoms. That's why they were so good for the gold foil experiment that Rutherford did. So we talk about a thing called effective nuclear charge. Effective means how well does it actually pull on those electrons? And of course, nuclear charge is the positive charge of the nucleus. We're looking at the outermost electrons primarily, but of course that pull is on every electron. And we now know how they're arranged in space with our orbitals and our sublevels. So what is effective nuclear charge? It comes down to two things. It is the number of protons. The more protons that you've got, the bigger the nuclear charge. So carbon has a bigger nuclear charge than boron, which has a bigger nuclear charge than beryllium, and so on. So the number of protons is going to, of course, determine how big our nuclear charge is. But having more protons pulling on each electron doesn't actually always increase the effective nuclear charge. And that's because as we fill energy levels, those electrons get further and further away from the nucleus. Otherwise, they get too congested. So adding energy levels creates a new complexity. So when I've got my electrons in a higher energy level, my outermost or valence electrons are at a much higher energy level, because they're a higher energy, they are further away from the nucleus. Distance is an issue. Just like if you think about magnets, the further away those magnets are from each other, if you pull them further away, the effect of their magnetic field reduces. They don't attract each other as much. But when you put them close together, they're really hard to pull apart. Same thing here. The effect of that nuclear charge on an electron out here is reduced because of distance. It's also reduced because to have an electron here, these two energy levels must be full. And so if I've got lots of electrons in here, then they shield it. It's like having a thin blanket in the way. So these are negative. What are they going to do to this electron here? They're going to repel it. Well done. So they reduce the effect of that nuclear charge because of a thing called shielding. So shielding is when you've got electrons in lower energy levels. They shield the effect of that nuclear charge. They reduce it. This is why atoms that are much further down the periodic table have much larger much larger radii, because they've got all these electrons shielding those valence electrons from the nuclear charge. So now we've got our two key things we'd have to discuss when justifying the shapes, the sizes of things. Then we need to know that there are a couple of trends, and this is the bit I said I lied about not adding. So what we notice is, as we go across the periodic table, I'll quickly sketch my periodic table in here. As we go across the periodic table, we're not adding any more energy levels. As we add more electrons, they're in the same energy level as the previous atom. But we are adding to the number of protons. So with more protons in there, but no more shielding, there's no increase in shielding, then we've got an increase here, no change here. This means my effective nuclear charge has increased, because this has increased, but this has stayed the same. So this has increased. That would mean if there's more a pull, what would that do to those outermost electrons? Would it let them get further away or pull them in tighter? Tighter, fantastic. So what we find is the radius decreases as we go across a period. But the opposite happens as we go down a group. And this shows you how important each of these two things are relative to each other. You are getting a lot more protons. But because you're adding an energy level each time, the amount of shielding undoes all the good work, as it were, of adding more protons. So it undoes that. So what you end up with is they get a lot bigger, actually, not just a little bit, but a lot bigger as you go down a group. Now, of course, there's going to be an exception. It wouldn't be year 13 without some exceptions and things that annoy us and have to remember. You're going to find some very interesting patterns in the transition metals as you go across, that they don't tend to get bigger at all. They tend to stay about the same as you go across in the transition metals. That's because when you add electrons, they're going in the third energy level and they're increasing a bit of shielding on the 4s electrons. So you're adding a proton and an electron, and they sort of cancel each other out. So you'll notice that a lot of the transition metals are very, each period are very, very similar. But the increasing down a group still works for the transition metals. Are there any questions before I stop that?